So the fifth section in the very big integration chapter is on a brand new strategy, a new technique. This is not adding on to stuff we already know or unwinding something, but it's a completely new approach to integration. It is really closely related to how we sorted out and used the chain rule, and essentially the strategy is that you replace your variable with a completely new variable in such a way that the integration becomes more straightforward to tackle. And the reality is that in your exam you will often be told which substitution to use, so you can generally rely on the fact that you're told what to do. There are a few instances where you're not told the substitution. In that case, it will be one of a series of reasonably obvious or standard substitutions that you can pick and have a go at. And as we'll see in some of our examples, sometimes there's more than one substitution that you could choose, which would give you the same result and still make life easier. So sometimes it's kind of up to you which substitution you need exactly. So I'm going to take you through this fairly straightforward example first, and I'm picking on this one because actually we've got three different strategies that will allow us to integrate this. It's not a hard integral to do. 1/3 of x plus 1 all squared. And the three strategies I can use are, well, two of them we already met. One is that it's just a polynomial. Okay, so what I mean by that is that 1/3 of x plus 1 all squared, well, I can just expand that out. It's just a binomial, so I'm going to get 1/9 of x squared plus 2/3 of x plus 1. So I can integrate x squared over 9 and 2x over 3 and 1, and we'll get x cubed over 27 plus x squared over 3, the 2's will cancel, plus x plus some constant. No problem, really easy actually. The second strategy you can use is the one we met earlier in the chapter. This is a function of a linear function, and therefore I can just use the strategy that we found earlier in the chapter. So the integral of 1/3 x plus 1 all squared is going to be, well, I divide by the derivative, which is the same as timesing by 3. So I'm going to end up with 3 lots of 1/3 x plus 1 cubed over 3 plus some constant. And this could do with a little bit of tidying up. Obviously the times by 3 and divide by 3 cancel. So actually I just need to expand this binomial, this cubic, and that's going to give me, well, it's going to give me 1 over 27 x cubed plus 3 lots of 1 over 9, so 3 over 9 x squared plus 3 lots of 1 over 3x, so 3 over 3x plus a 1. And actually what we can see is that this tidies up nicely to x cubed over 27, oh yes, I've got some c there, plus x squared over 3 plus x plus, oh no, that's interesting. Perhaps I should label this constant d and this constant d, because what we've ended up is 1 plus d. So this whole section with the letters in, with the x terms in, has turned out to be identical, but this constant has fallen out slightly differently from this constant when I do my expanding, but they are both constants. C and 1 plus d, they're both constants, and they will end up being the same. So I've got both. Both of those strategies involved expanding binomials. The second one was a lot simpler. It was a lot simpler to do, and actually I could have left this without expanding. I didn't need to expand this. We could have stopped here, 1/3 x plus 1 all cubed as our answer. And what I'm going to show you now is that there is a third strategy we can use for an integral like this, which will work really well, and it's called substitution. And the goal basically is to replace every single x for some u. And not directly, but we need to replace x's for some function of u. And the way we're going to do this is we're going to say u equals the function inside the brackets. 1/3 x plus 1. Okay, and that means straight away our integral now looks like u squared. So immediately this looks a lot better. But I do have a slight problem. I have an x still in my integral. And we can't do this. We can't differentiate u squared with respect to x. I need the same variable in both positions to actually do my integrating. It's just no good. So what I need to do is I also need to replace dx with something else to do with u. And the easiest way to think that through is, well, actually, we can find out what du by dx is. And du by dx is, well, it's 1/3. And if du by dx is 1/3, well, that gives us that du equals 1/3 of dx, or more helpfully, 3 dus is equal to 1 dx. So I can now replace my dx with 3 du. I need a little bit more space for this now. So this integral is now going to look like the integral of 3 u squared du, because I've replaced dx with 3 du. This is now really easy to integrate. So this is just 3u cubed over 3, or it's just u cubed. And then I plus c. Okay? And that's it. My integral is u cubed plus some constant. And if I want to replace that with the x terms, u is 1/3 x plus 1 cubed plus c. And I'm done. Now, there was a little bit of setup involved. I needed to choose a u and find du by dx to do all my swapping, but the integration step was incredibly quick, way quicker than expanding those brackets and dealing with it in that way. And this is the basic principle behind integration by substitution. You swap the variable out in such a way that the integration is easy. And which substitution you use is sometimes just given to you, and sometimes it's just a matter of having an intuition about a substitution that will be helpful in some way. Sometimes it's really obvious, sometimes less so. And we'll look at some examples now.